not interacting with your atomic positive core lattice, right, which is your lithium nuclei, right? They don't care about that. So it's very much like the ideal gas model for electrons. This is what free electron gas model means. So the word gas imply ideal gas, so it's kind of non-interacting type. And that corresponds to this picture that, you know, the electron can move freely in this. And this is why, you know, and in fact this electron is quite good because this is how battery work, right? Or why people love lithium is because you can actually use free electron gas model to simulate, to understand, you know, how the electron move in the lithium lattice. And this is what we got, all this lithium battery that we use on a daily basis. So in this model, weakly bound electron move about freely in the volume of the metal, and the valence electron become the conducting electron, right? It's not the conduction band, but the conducting electron, the electron that move around under the force, right? And the force between conduction electrons and the iron core are neglected. In other words, you have this iron core, right? You have this lithium iron core, right? Like this, or in some lattice. The electron, you think of the electron just move around. This electron that you got in the solid, doesn't matter which one it belongs to, which atom. But if you apply potential, they just move around. They don't get attracted. They don't get held back by your lithium iron core. Once you apply potential, they will just move like this. So that's the picture. So in this case, what does it mean? It means that if you try to calculate the energy of these electrons, you can ignore the potential energy. Potential energy are the electrostatic potential between the electron and the positive core that you got here. You can ignore read the potential energy term to 0, and you just left with the kinetic energy term. And that becomes very easy to solve, right? And this work for experiment that only depends on kinetic energy. Okay, kinetic energy. So what I'm going to do is that so this is our starting point, free electron gas model, free electron. And then we're going to talk about, so I'm going to give you a quick rundown of these physics way of looking at particle in a one-dimensional box, and then particle in a double one-dimensional box, two one-dimensional box, and then you can extrapolate into infinite dimension, the infinite number of one-dimensional box, right? And that is a linear lattice, right? So once you got that, then you can see the pattern of how these band structure emerge. So I'm going to break away and talk a little quickly about these quantum mechanics picture on this very handwritten notes that I have. So let me try to see how I can follow this. Okay, so again, if you have problem understanding it, don't worry too much about it. Those who could follow, then it's good, but I want people to realize the end results. I am actually not going to solve it. I just want to point out some strategic point if you were to go through quantum mechanics and calculate these things. This note is also on I believe on the website as well, if you can understand my handwriting, very bad handwriting. I apologize. So we start with, as with most quantum mechanics, you start with Schrödinger equations that we learned in first year course, and time independent Schrödinger equations, which is very simple, which is just a differential equation. So you have an operator and operating on wave function, and then you have energy, which is a constant, times a wave function, right? So this is a basic Schrödinger equation. And this Hamiltonian here, H operator, consists of two of them, the kinetic energy operator and the potential energy operator, right? So for free electron, we just talked about free electron gas model. We set the potential energy operator to 0, right? So then it becomes very simple. You just have the kinetic energy term, and in quantum mechanics, you write the kinetic energy operator as a double differential, right? So it's like some constant minus some constant minus h bar square. H bar is of course this Planck constant divided by 2 pi. That's the notation, and then you basically you have a constant, you have a double derivative, right? And the wave function and a constant and a wave function itself. So it's solving a second order homogeneous differential equation. Okay, so that can be solved. We learned this whenever we take the first differential equation class. We always deal with this kind of equation. And we know from math that the solution for this kind of thing is what the physicists call two plane waves, right? A linear combination of two plane waves. So you have one plane wave e to the I k times x, right? We are talking about one dimension. So if you're talking about 3 dimension, that would be k dot r is a dot product, but one dimension is nice, it's easy. It's just a constant times k. And this k here is the wave vector, direction going along the positive x direction. And then you of course have the opposite one. Okay, so you have forward and backward wave, right? These are plane wave, e to the I k dot r. It's called plane wave because if you expand this imaginary number, e to the minus I a, for example, you can write it as sinusoidal, right? So if you I theta is equal to cos beta plus I sine, like this, right? So that's sorry. So this is usually what you can expand by the Euler, so-called Euler equation that you got like this. So this is just shorthand. Think of it as plane wave because they are sinusoidal waves, right? Moving across your space in this k direction, right? This is identify your vectors in that direction, frequency, if you like. And so if you take this solution and substitute in this differential equation, what do you have? What you can solve is that you can solve for the energy, right? So the energy is what you're after. So the energy is equal to this constant times k square, and k square is just equal to 2 pi divided by lambda, and corresponding to exactly the de Broglie wavelength. So this is the wave vector. This is why it's called wave vector, because it's corresponds to the inverse de Broglie wavelength in that case. And this energy term is in fact in common look like 1/2 mv squared because h pi the momentum in fact is h pi k, right? H pi k. So you can actually get the energy, which is p squared divided by 2m, right? So the energy is just equal to p squared divided by tm, which is the same as the kinetic energy that you got. Okay, so this corresponds to 1/2 mv squared. So that's the solution. That's it. It's very simple, and this is for free electron. We understand, and what happened here? What happened here is that there's no condensation, right? Because this energy can take on any value, right? Take on my k can be anything. There's no restriction because it's a free electron. Because there's nothing to restrict the movement of my electron. So there's no boundary condition, and so this k can take on any value. It's a continuous change, right? The energy of paradox is not quantized, so that's the key point that if you do quantum mechanics, which is what you expect as in classical mechanics for free electrons. And now, if you look at very quickly on the electron in a single square well, so you have you put the electron not free, not allow it to move in anywhere in space. You put it in a potential like this between L0 and L. This is called a square well, one-dimensional square well. And you define this potential in this way. So this is my V, or so here we have my U, which is my potential energy operator, is 0 inside the well, right? 0 when x, this is x. When x is between 0 and L, no potential energy, right? The electron is free inside here. But outside the well is infinite. So once you put the electron inside, the electron is trapped. It cannot escape. It's just trapped inside as well. Okay. And so the equation in the well, right? So you solve it in different regions. So let's solve it inside the well first. The equation in the well, because inside the well the potential is